Ever feel like you're drowning in technical docs? Just wishing you could get the core stuff fast.
Yeah, totally. Information overload is real.
Well, that's what we're doing today. We're diving into something pretty fundamental in Kubernetes, but maybe a bit overlooked sometimes, the replica set.
That's right. It's kind of an unsung hero. Our mission here is simple. Demystify replica sets. What are they? Why do they matter? And how do they actually help keep your applications running smoothly and scaling properly in Kubernetes?
Okay, let's unpack this then. What exactly is a replica set? And, why should we, or anyone running apps, really care? I get the feeling it's about keeping things, well, available.
You basically hit the nail on the head. At its heart, a replica set is a Kubernetes thing, a resource whose main job, its only job really, is to make sure a specific number of identical application copies or pod replicas are always running.
Okay, replicas meaning copies of my application instance.
Exactly. I think of it like a very dedicated manager. It constantly checks, do I have the number of pods the user wants? If not, it creates more. If there are too many, it gets rid of the extras. It's all about matching the desired count.
That sounds incredibly useful.
Yeah.
But why the need for this automated manager? What core problems does it solve? Is it just about preventing crashes, or is there more to it?
Oh, much more. Imagine trying to manually keep, say, 5 copies of your web server running perfectly. One crashes, you have to notice, log in, restart it. It's messy and slow.
Right, doesn't scale.
Not at all. So, replica sets give you reliability. A pod dies, maybe the whole node it's on has issues. The replica set controller sees it's short and spins up a replacement automatically. No human needed.
Ah.
Then there's scalability. Need to handle more traffic. You just change one number in the replica set definition, say from 3 replicas to 10, and boom, Kubernetes starts creating the new pods. The automation is key too. You declare what you want, Kubernetes figures out how. And finally, resilience. It doesn't just replace failed pods, it ensures the new ones get scheduled onto healthy nodes in the cluster.
So it's like this background guardian constantly ensuring the right number of my app instances are healthy and running. Fewer 3 a.m. pages, maybe?
That's definitely the goal.
Now, just quickly, before we get deeper into how they work, can we ground this in a couple of key terms? We keep saying pod. It's the smallest thing we deploy, right? Like one instance.
Correct. A pod is the smallest deployable unit in Kubernetes, usually containing 1 or more application containers.
And you also mentioned deployments. How do they relate?
Good question. Deployments are actually a higher level resource. Very often, you won't create replica sets directly. You'll create a deployment, and the deployment will manage replica sets for you. We'll definitely come back to why that's important.
Okay, got it. Pods, deployments. And this all happens within the Kubernetes cluster.
Right. The cluster is your pool of machines. You typically interact with it using the kubectl command line tool, sending instructions to the central API server, which is like the brain of the control plane.
All right, this is where I think it gets really interesting. You said declare what you want, that declarative model.
Mm-hmm.
Can you expand on that? How does a replica set actually use that idea? It feels different from, scripting every single step.
It absolutely is a different mindset. Instead of writing a script saying create pod 1, check if it's running, create pod 2, you write a definition, usually in a YAML file, that says, I want 3 pods that look like this. That's the desired state.
And Kubernetes just makes it happen.
Pretty much. The replica set controller is constantly watching. It looks at your declaration, the desired state stored via the API server, and compares it to the actual state of the cluster. Are there 3 pods running that match the description? If only 2 exist, it creates 1 more. If 4 exist somehow, it terminates 1.
So it's this continuous loop of check and correct.
Exactly. A reconciliation loop, bringing reality in line with your intent.
Okay, so let's peek inside that YAML file then. If I were defining a replica set, what are the absolute must-have pieces in that configuration?
You'd see a few main parts. First, APA version. For replica sets, that's typically apps v1, tells Kubernetes which version of the API definition to use.
Standard stuff.
Yep. Then kind, which simply says replica set, no surprises there. After that, metadata. This holds things like the name you give your replica set, maybe a namespace if you're organizing things, and importantly, labels, which are key value pairs you attach for identification.
Labels for finding it later, I guess.
For finding it, and crucially, for linking it to the pods it manages. That comes next, in the spec section.
Ah, the spec. That sounds like the core of it. What's in there?
It really is the heart. The first key field in spec is replicas. Just a number. How many copies do you want? 3? 5? Whatever you need.
Simple enough.
Then, crucially, the selector. This tells the replica set which pods it's responsible for. It uses label selectors, basically. It says, I manage any pod that has these specific labels.
Ah, so the labels in the metadata and the selector need to connect.
Well, the selector in the replica set spec defines which pod labels it looks for. Then, the pods themselves need to have those labels. This happens via the template section.
Okay, what's the template?
The template is nested inside the spec. It's literally a blueprint for the pods the replica set should create. It contains its own metadata, including the labels the selector will look for, and its own spec, defining the containers, the image to run, like Nginx, or your custom app, ports to open, and so on. It's a full pod definition embedded within the replica set definition.
Right, so to recap, APR version and kind are boilerplate. Metadata names and labels the replica set itself. Spec contains the desired replicas count, the selector to find the pods by label, and the template, which is the pod definition, including the matching labels.
You've got it. That structure allows the whole system to work.
And connecting this back, this declarative approach using YAML, controller constantly watching. That's what gives us the consistency, the easy scaling just by changing that replicas number, and the automatic recovery when things fail.
Exactly. Let's use that web server example again. You define a replica set. 3 replicas using the Nginx image label app.webserver. You apply it. Kubernetes creates 3 pods with that label.
Okay.
Now, if one pod crashes or someone accidentally deletes it, the replica set controller notices, hey, I only see 2 pods with app.webserver, but I'm supposed to have 3. So it uses the template to create a new one. Back to 3, seamlessly.
That self-healing aspect is really powerful. Okay, stepping back again, we have this YAML definition. Where does it go? How does it interact with the rest of the Kubernetes system to make those pods appear?
Great question. It starts with you using kubectl-apply-fur-replicaset.yaml. That command sends the YAML definition to the Kubernetes API server.
Dexter's front door.
Precisely. The API server validates your YAML checks if it's structured correctly, uses valid fields, etc. If it's okay, it stores this definition in etc., which is the cluster's persistent key value store. Think of it as the system's source of truth for desired states.
So etc. holds the I want 3 pods instruction.
Exactly. Now, the ReplicaSet controller, which is just another process running within the Kubernetes control plane, is constantly watching the API server for changes and for the current state of things. It sees this new ReplicaSet definition appear in, etc.
And it compares desired versus actual.
Yes. It checks how many pods currently exist that match the ReplicaSet selector. Let's say it's 0 initially. It knows it needs 3. So it tells the API server, I need to create 3 pods based on this template.
Who decides where those pods run?
Ah, that's the job of the scheduler. Another control plane component. It sees these pending pod creation requests. It looks at the available nodes, the worker machines in the cluster, considers their resources, CPU, memory, any constraints you might have set, and decides which node is the best fit for each new pod.
Smart place.
Then, once a node is chosen, the kubelet, which is an agent running on every node, gets the instruction for that specific node. Start this pod configuration. The kubelet pulls the necessary container images, like Nginx, starts the containers defined in the pod template, and then continually reports the pod status back to the API server.
Wow, quite a chain reaction. From YAML to running a container involving the API server, etc., controller, scheduler, and kubelet.
It is, but it's what makes the whole system automated and resilient.
Okay, that makes sense. Now, earlier you mentioned that we usually don't manage replica sets directly. We use deployments. Why is that? What does the deployment add on top?
This is super important for practical, everyday use. While you can create a replica set directly, deployments provide crucial application lifecycle management features on top of replica sets.
Such as?
The big one is updates. Imagine you want to release a new version of your application. With just a replica set, managing that update smoothly is tricky, but a deployment handles it beautifully using strategies like rolling updates.
How does that work?
When you update the pod template within your deployment, say, changing the container image version, the deployment doesn't just modify the existing replica set. Instead, it creates a brand new replica set with the updated template and a desired count of 0 initially.
Okay.
Then, it carefully orchestrates the rollout. It might scale up the new replica set by 1 pod, wait for it to be ready, and then scale down the old replica set by 1 pod. It repeats this process, gradually rolling the update across your instances, ensuring your application remains available throughout the entire update.
0 downtime updates. That's huge.
Absolutely. And what if the new version has a bug? Deployments also manage history. They keep track of the previous replica sets. If you realize the update is bad, you can easily tell the deployment to roll back, and it will reverse the process, scaling down the new replica set and scaling the old, stable one back up.
Okay, I see now. Deployments use replica sets under the hood,
Yeah.
but add that critical layer of controlled updates and rollbacks.
Exactly. Deployments manage replica sets. You typically manage deployments.
So, summing up the effectiveness then. Replica sets provide the core guarantee of running X copies, giving automation, basic scaling, and resilience. They manage pods using those flexible labels.
Correct. They are the foundational workhorse for ensuring instance count.
And the best practices really flow from that relationship with deployments, right?
Pretty much. First, absolutely prefer deployments for almost all stateless application workloads in production. Don't manage replica sets directly unless you have a very specific niche reason.
Makes sense. What else?
Use clear labels. Be intentional about the labels on your pod templates and the selectors in your replica sets or deployments. This is how everything links together. Good labels make management much easier.
Good hygiene.
Definitely. Also, monitor resources. Just because you ask for 100 replicas doesn't mean your cluster nodes have the CPU and memory to actually run them effectively. Keep an eye on node capacity.
Right. Reality check.
And finally, always use version control for your YAML files. Store your deployment and replica set definitions in Git or a similar system. Track changes, collaborate safely, and make it easy to revert or see history.
Solid advice.
Yeah.
So we've really peeled back the layers on replica sets today. They're clearly not just some minor detail. They're fundamental to Kubernetes, ensuring your applications have the required number of instances running, providing that core reliability and scalability.
Absolutely. And understanding them, especially seeing how they fit underneath deployments, is key to building robust fault-tolerant systems. It's really a cornerstone of how Kubernetes delivers on its promise of highly available applications.
You know, thinking about this whole process, defining a desired state in YAML, having controllers automatically work to make it reality, the self-healing,
Yeah.
it makes you wonder, how could these ideas of declarative management and automated resilience apply elsewhere?
That's a great thought.
I mean, beyond Kubernetes. Could you apply that thinking to other complex systems? Maybe even, managing personal projects or workflows, defining the end state and letting systems or habits work towards it.
It's definitely a powerful paradigm, declaring intent over specifying steps.
Something interesting for you, the listener, to think about. How might that declarative self-correcting approach change how you tackle things? Worth pondering.